Hello, ladies and gentlemen. As mentioned, my name's Blair Hammond. I'm an engineering technologist with the City of London, and I'm here to present my report titled Transatlantic Tunnel, an Alternative Approach to Global Travel. The concept for this report originally came from a Discovery Channel episode called Extreme Engineering, which I further researched and expanded on for my technology report. So as the title indicates, this report involves the construction of a tunnel that traverses the Atlantic Ocean by means of new and innovative technology using magnetically levitated trains as the method of transportation. So I examined some current magnetically levitated trains in operation today, such as the Shanghai China maglev train that was the first to become operational to the public in 2003 and was the fastest train at that time. Another maglev train is in Daejeon, South Korea, which is a low-speed urban maglev designed for use within urban settings. And finally, the Japan Yamanashi superconducting maglev shown here on the test track. The technology used on the Japanese train differs from the other two, which I will get into. So electromagnetic suspension, or EMS, is the technology used on the Chinese and South Korean trains. This design involves magnets attached to the train oriented towards the track. The electromagnets in the train attract the magnetically conductive track to levitate and propel the train cars. Magnetic interaction varies with distance and must be constantly monitored and adjustments made. The rail is situated between the upper and lower edges of the undercarriage. Some EMS systems can provide both levitation and propulsion by use of onboard linear motors. So as shown here in these pictures, the train undercarriage wraps around the magnetically conductive rail called a guideway to provide onboard levitation, guidance, and propulsion. Versus the alternative, which is electrodynamic suspension, EDS, which is the technology used on the Japanese train. This design involves the guideway and train exerting a magnetic field which levitates and propels the train by repulsive and attractive forces. The magnetic field in the train is produced by superconducting magnets. These are magnets made out of materials that can be cooled to cryogenic temperatures so that all electrical resistance is removed, classifying them as superconducting. So some major advantages over the EMS technology are that this design is naturally stable and requires no corrections or adjustments to be made, allows for much greater separation between the guideway and the train, and is much more energy efficient due to the superconductivity of the onboard magnets, eliminating any resistance to the electrical current. So some disadvantages. At low speeds, the vehicle must have wheels to travel on, requiring additional infrastructure and maintenance costs. Due to the propulsion coils required throughout the alignment of the guideway, this design is more costly. Now here you can see the elements of the EDS Guideway, the wheel support paths, the electromagnetic coils housed within the guideway beams. And here, this is the internal workings of an EDS maglev. Some of the key elements I previously mentioned are shown. The superconducting coils are identified along with the liquid nitrogen and liquid helium containers, which attach to the compressor unit to provide cooling of the superconducting magnets that are housed in the bogie frames on the sides of the train. The auxiliary supporting and guiding gear can also be seen for use at low speeds. This image depicts the natural state magnetic interaction between an EDS train and its guideway, showing as the forces remain constant, the entire train and its guideway function as one magnetic field. So if the train begins to deviate closer to either beam of the guideway, the repulsive and attractive forces react correspondingly to ensure the train remains on course. Due to the advantages EDS technology offers and the high rates of speed achieved by these trains, I've selected the JR-MLX-01 superconducting maglev, or SC maglev for short, as the train to operate within the transatlantic tunnel. This is the train used on the Japan Yamanashi test track, which is shown here, and holds the the record for fastest speed achieved by a manned train, which is 581 kilometers an hour. And here you can see the displays of the liquid helium and liquid nitrogen compressors and the bogie frame that contains the superconducting magnets. And this is another image of the MLX-01 SC maglev. You can notice the sleek body design of the end cars for aerodynamics. And the next image shows a cross-sectional view of the undercarriage of the train. The electromagnetic coils in the guideway beams can be seen. Adjacent to them on the train are the superconducting magnets, which interact with them. So some major benefits of magnetically levitated trains are that they're environmentally friendly, as they produce no emissions. Much less maintenance is required compared to conventional trains, as none of the moving parts come into contact with each other than the wheels at low speeds. And they are much faster and quieter than other methods of transportation. Okay, so now that we've looked at the mode of transportation that will be incorporated within the transatlantic tunnel, I'll talk about how the tunnel will function. Passengers will travel across the Atlantic Ocean from New York City, USA to London, England on board a JR MLX-01 SC magnetically levitated train, enclosed in an airtight tunnel structure. So the tunnel alignment was mapped out for both the horizontal and vertical positions. 2 horizontal alignments were considered. The first is shown in red, which is in a straight alignment, 5,200 kilometers from New York to London, England. And the alternative is in yellow, which is a route that would head north to the southern tip of Greenland, then passing by northern England and ending in Norway, 6,800 kilometers. Due to the additional infrastructure required, the extra 1,600 kilometers in this route and extra docking stations that would be necessary, the straight alignment from New York to London, England was chosen. So the vertical alignment offered a variety of possible options. A floating tunnel above the ocean surface was considered. A tunnel fixed to concrete pillars extending from the sea floor was also contemplated. And finally, a tunnel submerged 150 feet below the ocean surface, fixed to the sea floor by long steel tethers that attach to the sea anchors formed in the seabed below. This was the vertical alignment which was chosen as it provides the most advantages. So with this tunnel location, the structure will not be affected by the unpredictable surface of the Atlantic Ocean. It will not impact sea vessels or aquatic life and minimizes the amount of infrastructure required for support. Now, there's one common limiting factor that all modes of transportation have in common, and that is frictional resistance due to wind. The transatlantic tunnel will be depressurized by use of large vacuum pumps to remove wind resistance within the tunnel. As the design for the superconducting magnetically levitated train does not include any moving parts that come into contact with each other, and we have removed any resistance caused by air pressure, this train could theoretically accelerate at a constant rate of speed until there is no more guideway available for it to travel down. So here's a view of the overhead speedometer you will see when riding the Chinese maglev train in Shanghai. It is traveling at 431 kilometers an hour, but while riding the transatlantic tunnel, passengers will look up and see this. When traveling at top speeds in excess of 4,000 kilometers an hour. This trip would take a total of an hour and a half to travel the 5,200 kilometers. That allows for 12 minutes of acceleration from 0 to 4,000 kilometers an hour over a distance of 400 kilometers, then an hour and 6 minutes at the top speed to travel 4,400 kilometers, and finally 12 minutes of deceleration, which would take you the last 400 kilometers of the trip. These acceleration and deceleration rates would expose passengers to relatively the same amount of G-forces as currently operating trains. So some of the key tunnel elements include the anchors and steel tethers that will be used to fasten the tunnel's structure to the ocean floor and prevent it from moving. These anchors will be formed into the ocean floor, and this can be done by divers as seen here at shallower depths, but robotics will need to be used for construction and maintenance of the sea anchors in the deeper depths. The site locations for the sea anchors were selected to maximize the points of contact between the anchors and the tunnel structure, but minimize the depths at where these locations occur. So there are many distinct and identifying features found on the ocean floor, such as continental shelves, mid-ocean ridges that experience earthquakes, as well as low-lying abyssal plains and trenches. This is the ocean floor profile between North America and Europe, where many of these ocean features exist. In red are the ideal locations for the sea anchors at the high ridge points. And here in yellow are the low-lying trenches and abyssal plains that must be avoided. The tunnel structure itself will contain buoyant material to ensure it naturally wants to float to the surface. It will then be fastened to the ocean floor, preventing this lift-up effect. However, in addition to resisting uplift, these tethers and anchors will also need to account for the ocean currents. The strongest ocean currents the transatlantic tunnel will be exposed to are the Gulf Stream current and the North Atlantic current. So the tunnel uplift will want to bring the structure in a vertical direction. The ocean currents will want to take the structure in a horizontal direction, and all of this will be resisted by the steel tethers, ensuring the alignment does not deviate. So another element of this tunnel design are the immense vacuum pumps, like the ones seen here. They would need to be transported to the docking stations to depressurize the tunnel from each end. Here's a more detailed cross-section showing the concept of the transatlantic tunnel. 2 trains will operate on the primary guideway in the middle. A third train will operate independently as needed down in the below compartment on an auxiliary guideway, and a maintenance shaft or service port will be provided in the top section for access. The design will include large gaskets between each tunnel section to ensure the tunnel remains air and watertight. There will also be steel beams acting as dowels that extend through multiple tunnel sections to transfer loads evenly throughout the entire structure. Also shown here are the power sources running to each guideway and the steel tethers. The transatlantic tunnel will be exposed to corrosive salt water, and this can be very detrimental if the proper admixtures and alloys are not used. High-crete admixtures used in concrete applications are proven to protect against water ingress and saltwater corrosion. This would be used on all of the exposed concrete structures, such as the sea anchors. And some steel alloys that do not corrode in seawater will need to be used for the outer structure. Stainless steel alloys have proven successful when used in saltwater applications, and we are envisioning similar alloy compositions as those used in desalination plants to be incorporated with this design. So the tunnel construction will be constructed out of 54,000 prefabricated steel sections. These will be approximately 96 meters in length, fastened together with gaskets. These prefabricated tunnel sections would be loaded onto ocean barges and transported to on-site workstations called immersion pontoons. The immersion pontoons would be used to lower the tunnel section 150 feet below the surface to the tunnel alignment, awaiting connection to the main structure, and for a temporary cap to be installed. The immersion pontoons would function as mobile workstations, traversing the Atlantic Ocean with the construction of the tunnel, initiating from each coastline and connecting the final piece somewhere in the middle of the Atlantic. So this design was considered in terms of initial costs, and a rough estimate was established based on comparisons with other existing tunnel projects and magnetically levitated train projects. The Shanghai China maglev train cost $10 billion US and is 30.5 kilometers long. The Japan Yamanashi test track costs $91 billion US and is 42.8 kilometers long. So the transatlantic tunnel is estimated to cost $12 trillion and would be 5,200 kilometers long. The last thing considered were possible safety or contingency measures that would be used with this tunnel. Current safety measures used on magnetically levitated train technology would be maintained, such as monitoring seismic activity and, if required, performing emergency shutdown procedures. Since the tunnel will be depressurized, each train car will have a separate cabin pressure system similar to an airplane, and each train would be equipped with this. They would also have GPS sensors and onboard emergency mechanical propulsion systems. This would allow, in the event of a catastrophic failure of the tunnel, the immersion pontoons that normally are used for standard tunnel maintenance to perform emergency rescues by isolating and removing the tunnel section containing the maglev train. Then the train cars under separate cabin pressures can utilize their onboard mechanical propulsion systems to maneuver to safety. So my conclusions were that the transatlantic tunnel is not currently feasible due to the astronomical amount of raw materials required and financial resources. However, as maglev technology becomes more accessible and efficient, society's influence on governments worldwide to reduce pollutions and emissions grows, and environmental concerns continue to drive change, the transatlantic tunnel may one day become a possibility. And my recommendation is that a maglev train tunnel of a smaller scale be constructed to act as a case study to better understand the capabilities and limitations. Perhaps a tunnel across Lake Ontario connecting Toronto with the United States. All of my technical references for the presentation and the report are here. And that concludes my presentation. Thank you very much.